Very good evening to all my students. In this session, we are going to see about constructional details, working principle, and types of synchronous reluctance motor. First, constructional details. Generally, all kind of electrical motors having two major parts such as stator and rotor. The stator is a static part and rotor is a movable part. First one, stator. The stator has one stator core and the main part such as winding. The stator core manufactured by several number of laminated silicon sheets by stamped together and the winding designed by using copper conductors. Then the types of slots. In this kind of machines, we can prefer two types of slots such as open slot and semi-closed slot, but the most preferable one is semi-closed slot because when we go for open slot, which it leads huge harmonics and some significant torque pulsations also. So the semi-closed slot is the most preferable one in this synchronous reluctance motor design. The next one, rotor. Normally, a salient pole rotor is most preferable one for the synchronous reluctance motor. We can use cylindrical type rotor, but the salient pole rotor is most preferable one because the main working principle is depends synchronous reluctance variations, so that salient pole rotor is most preferable here. In this rotor having no windings and there is no permanent magnet also. So this rotor just like cage rotor which used in squirrel cage induction motors, but instead of solid bars which used in induction motors, here some ferromagnetic materials or some aluminum materials used, and by using explosion bonding technique the rotor has designed. Then operating principle of synchronous reluctance motor. First we should provide three-phase symmetrical winding in this synchronous reluctance motor which to be excited. Then already I told that the rotor has no windings, so we can use salient pole rotor as well as cylindrical rotor. Here cylindrical type rotor shown in this figure, but the most preferable one is salient pole rotor. This is the basic torque equation for synchronous reluctance motor. In this equation, P is nothing but number of poles psi s, stator flux linkage, LDS and LQS are the direct axis and quadrature axis inductance, and del is nothing but torque angle. So by using this expression we can discuss how the machine synchronous reluctance motor performs. Here rotor has no windings, so at the initial condition this synchronous reluctance motor starts as normal induction motor by induction principle. After the motor reach its around rated speed, more than 90%, you can say more than 90% or 85 percentage, then the same synchronous reluctance motor can act as a normal synchronous motor. So this is a combined characteristics of synchronous reluctance motor and induction motor. Then we know under running condition this synchronous reluctance motor runs as normal synchronous motor. So the speed of revolving magnetic field which developed by the stator and rotor poles are synchronized themselves, but even though they synchronized themselves, there is some torque angle, that is the rotor poles somewhat lagging compared with the stator poles, so some torque angle always being there. Then it is possible to get a maximum torque at 45-degree torque angle. So By adjusting the LD/LQ values, we can change the torque angle. So by adjusting those LD/LQ value, we can attain the maximum torque. Then locked rotor torque also possible, which leads to cogging problems. This cogging problem also presents in this normal synchronous machine, we know. Then by providing some special arrangements, we can avoid these cogging problems, such as skewed rotor provision. Then another one is then rotor slots should not equal to stator slots, and the relationship between rotor slot and stator slots must be a round number. There is no fraction number, so that should be round number. And when the synchronous reluctance motor act as an induction motor at the time of starting, the power factor and efficiency are very poor, because it develop some starting torque. For developing that huge amount of starting torque, the machine will draw much starting current, so that losses will be higher at the time of starting. Then, when the machine acts as a normal synchronous motor under running condition, normal synchronous motor, it has high power factor and high efficiency. So much improved under running condition compared with starting conditions. Then the main advantages such as low cost, robustness, reliability, and able to operate at low frequency. These merits are listed compared with normal synchronous machines. Then there is a disadvantages also. That is, the machine draws much current at the time of starting, which leads higher losses. Already I told, for developing huge amount of starting torque, the machine try to draw much starting current from the main supply, so that the losses will be higher here, and efficiency will be low. That is the main drawback in this machine. It is also main drawback in most of machines. Then the applications, recording instruments, many kind of timers, signaling devices, phonographs. In those kind of variable speed applications, we can use this synchronous reluctance motor. Then classification of synchronous reluctance motor according to rotor configuration. There are two possible configurations, such as cage rotor and cageless rotor synchronous reluctance motor for variable speed. First one, cage rotor synchronous reluctance motor for line start. Line start means the input voltage and frequency are constant. That's why you can say line start. There is no pulsations, there is no variations in the input voltage and frequency. In those kind of constant supply applications, we can use this kind of cage rotor synchronous reluctance motor. The diagram for the cage rotor synchronous reluctance motor are shown here. Then cage rotor synchronous reluctance motor for line start, the rotor slot area here that proportional to q axis magnetizing inductance LQM. So when we change the LQM value, we know that the torque angle will be varied. So by adjusting the LQM value, we can change the torque angle as well as torque values. And another relationship here, the starting torque that proportional to the variation, the difference between LD and LQ values. Then segment solid iron rotor construction here shown in this figure. Then cageless rotor synchronous reluctance motor for variable speed. Here the diagram shown for a cageless rotor. Here there is no windings, so it just looks like solid condition. The diagrams are shown here. These kind of rotors can used for constant power speed range. Then classification according to the magnetization or lamination of the rotor. There are two types, such as axial air gap motor and radial air gap motor. When we want to get more power factor and good efficiency and good torque application, we can prefer axial air gap motor. Then second one, radial air gap motor. By using this radial air gap motor, we can reduce the torque ripple and iron losses. First one, axial air gap motor. In this axial air gap motor, many laminations are provided in vertical directions, which shown in the figure. The some amount of aluminum sheets also here used. The thickness of those aluminum sheets or zero point 0.2 mm, and by using this axial air gap motor, we can attain around 94 percentage of efficiency. That is maximum possible efficiency under this axial air gap motor. Then in this rotor, ferromagnetic and non-ferromagnetic materials are used. Those ferromagnetic or non-ferromagnetic seeds are placed alternative. Then by providing the number of seeds which is equal to number of rotor poles, we can get the minimum reluctance in this air gap axial air gap motor. Then axial air gap motor with the flex barrier type. So in this flex barrier type, the LD/LQ value is very small, as well as the Q axis air gap much greater than D axis air gap. So by using this axial air gap motor with flex barrier type, we can improve the circulating fluxes in the pole faces. These are the figures for air gap axial air gap motor with the flex barrier type. Thank you.